Suresh is a college-going student. He normally returns home after college at around 5 pm. Sometimes he returns at 5:05, sometimes at 4:50 pm. Sometimes he gets stuck in the traffic and returns around 6 or 6:30 pm. And if there happens to be an off period, he returns early, say 4 pm. So, Suresh does not return home exactly at a certain time point. His time of return varies, and therefore his time of return is a variable. Let's call it t for time. Since t is a variable, in fact a continuous random variable, it will have a distribution. What does that mean? It means that if you collect data on his time of return over long periods of time and generate a histogram, then it may look something like this. You can readily make out that on vast majority of the days, he returns home at around 4:30 to 5:30 pm. But occasionally, his time of arrival could be as late as 6 to 6:30 pm or even as early as 3 to 3:30 pm. The same data presented in form of a probability distribution tells you that on a given day, he is more likely to arrive close to 5 pm. The mean being 5 pm. The probability of his return decreases as one moves in the negative and positive direction relative to the mean. This is a hypothetical model of Suresh's time of return in form of a probability distribution. What we have just discussed is merely the background. Now let's get to the problem. One day, Suresh returns home at 8 pm. His mother is obviously worried and would like to have him explain his late return. Maybe they think that this is abnormal, something is fishy or serious. Probably he went to a movie after college without their knowledge or got himself into a brawl with some goons on his way back home. But his father would like to take it easy. He says, well, he cannot be coming home exactly at the stroke of 5 every day, and because his time of arrival has a distribution, it is quite possible that all is fine and that it's just a chance event that he has returned so late. It can happen. This is where the problem lies. The parents are caught in a dilemma. Either something is wrong or all is well. To ask or not to ask for an explanation. If they agree that this was a chance event and this could happen on any given day, they would not be worried. If they agree that there is something wrong, which is the cause for the late arrival, then they would ask for an explanation. Please note, the view that something is wrong arises not only if Suresh comes late, but also if he is too early. For example, if Suresh is back at 2 pm, that may also raise suspicion. Perhaps he was sent back home because of misbehavior. Or maybe due to some emergency, the students were asked to go back home early. Therefore, abnormality or departure from the normal can happen on both sides of the mean time of arrival. So there are two views. All is well and something is wrong. The parents have the task of deciding which view to accept. That is what hypothesis testing is all about. Their subjective opinion does not matter. They have to take one of the sides. That is, accept one of the views, and that too objectively. Please note that after analyzing the matter, whichever view they accept may or may not be the truth. There is probability of an error, but we will talk about that later. For now, we will discuss how to go about deciding which view to accept. Before we look at it technically, let us first have an intuitive idea. In this example, it is right that any time of return is possible with a small or large probability. But then, for taking a decision, where do we draw the line or the threshold? Here, or there? Which time of return is too early or too late to cause suspicion or alarm? For example, you may set the threshold as shown in this slide. You may say, if the time of arrival is in the red zone, then I will say that something is wrong. If it is in the green zone, you may say that nothing is abnormal and all is well. So it is a question of how far from the mean you would set the thresholds. Let us see how that is done. The first step is to state the two hypotheses. In this example, the null hypothesis, which is denoted by H0, is that all is well or the situation is as usual. By convention, a null hypothesis is the one which maintains status quo. The alternative hypothesis, on the other hand, stated as HA, is something is wrong or something is different or unusual. The second step is to first assume that the null hypothesis is true, in this example all is well, and then find the answer to the question, which is as follows. Given the null hypothesis is true, that is all is well, what is the probability of the given observation or any observation equally or more extreme than this? In this example, what is the probability of Suresh arriving at 8 p.m. or any time after 8 p.m. if everything is fine and all is well? But that's not all. One has to find out the probability of the other equally or more extreme event. That is, Suresh arriving at 2 p.m. or earlier. Remember what we discussed earlier, that departure from normal is not only when Suresh comes too late, but also if he comes too early. Therefore, one must find the probability of Suresh returning at 8 p.m. or later, or 2 p.m. or earlier. That is, the probability of arrival time in the red zones shown in the figure. If that probability is so low that the observation under consideration could not have happened by chance alone, if the null hypothesis is true, that is, in this case, if everything is normal, then one rejects the null hypothesis and accepts the alternative hypothesis. So, the objectivity lies in the determination of the probability value. That leads to an important question. What is the probability threshold below which we consider the probability of the observed event to be too low to reject the null hypothesis? Well, in most studies, the threshold is 5%. This is also called the level of significance, meaning if the probability of the observation or an equally or more extreme observation is less than 0.05, you say that the probability is so low that the observation cannot happen by chance alone if the null hypothesis were true. That means there is some definite reason behind this extreme observation. That sets the criterion for rejecting the null and accepting the alternate hypothesis. Else, if the probability of the observation or an equally or more extreme observation is not less than 0.05, then you say that there is no sufficient evidence to consider that something is wrong, and the observation could be a chance event. Thus, you accept the null hypothesis. In this example, if the probability of Suresh coming at 8 p.m. or later or 2 p.m. or earlier is less than 0.05, then reject the null hypothesis and accept the alternative hypothesis. Meaning that you will go with the idea that something is wrong, because your argument is that if everything were normal and all right, then Suresh would not have arrived at this hour. His probability of arrival at this hour is so low that it could not have been a chance event, and that there has to be some serious reason behind his late arrival. On the other hand, if the probability of Suresh coming at 8 p.m. or later or 2 p.m. or earlier is not less than 0.05, then accept the null hypothesis. You say that nothing is unusual. The probability of his arrival at the given hour is not so low to arouse any suspicion. It was simply a matter of chance. So here is a quick recap of the procedure. State the null and alternative hypothesis, set the level of significance, calculate the probability of the observation or an equally or more extreme observation than that, assuming the null hypothesis to be true, If the calculated probability is less than the threshold, then reject the null hypothesis and provisionally accept the alternative hypothesis. And finally, if the calculated probability is not less than the threshold, then accept the null hypothesis. One final remark. The probability threshold is called the level of significance, as I said earlier. One can vary the level of significance. One can set it to 10% or 1% depending upon the situation, context, and the desired level of stringency. In another video, I will discuss an example based on coin toss that involves hypothesis testing.